Okay, good morning, everyone. Welcome back. Okay. Today we are going to kind of finish our discussion of random processes and noise, and this is the last material that will be on our exam, which is scheduled for a week from Thursday. Now we could move it to Tuesday and get it over with sooner. And maybe I will poll you about that. But as of now, it's scheduled for a week from Thursday. Here's how just to give you an idea, the exam, basically, we're not going to have class that day, but you will have, all day to do the exam. So it'll be posted in the morning. I will be available on the Zoom channel during class time if you have questions. But it'll be released in the morning or maybe even the night before, and due, before midnight or so on Thursday. Okay, you will not need all that time to do it. And if I was to estimate time, of course, some people will take as much time as they possibly can, from past experience, but it really shouldn't take you, more than maybe 2 hours. So should be doable during class time plus a little extra, but you certainly don't have to do it during class time. You can use any resources that are not people, basically. So you can look anything up on the web. You just can't contact any persons in any way. Certainly, you can email questions to me, and I can choose whether or not it's appropriate to answer them, right? Okay, so any questions on that aspect of the exam? No, before you ask, no, I don't post past exams. Because then people study the exam and don't try to learn the material. Okay. Best advice for preparing for the exam, even though it's, open resources, is, well, just make sure you have read through the solutions and maybe view the recorded solution discussions. And, you're familiar with all of the material we've talked about, basically. Okay, now opening up any questions right now about the exam. Well, obviously we'll have a couple more occasions to get together before that. So, okay. Anyway, that's what to look forward to. I will give you, since we used to do these exams in class, right? I generally had a first page of exam that had equations that you may find useful, and in this case, Fourier transforms. Now, every equation you find on that page is not necessarily going to be used in the exam. Basically, some equations you might need and some equations you don't need, and you should know the difference. Okay. Okay. And later on today, I think we will take a look at a sample question from a prior exam. But so assignment 3, I will, be grading today or tomorrow and recording a discussion of the solution and posting the solution for assignment 3. Now, where we left off was, well, we kind of left off with our discussion of Fourier space relationships with autocorrelation, okay? And the key things to remember there, right? Autocorrelation or autocovariance, and again, you should have some idea how they're related, only through the mean. Describe statistical relationships within a signal given time or distance apart. And so they, as a result, they influence the features in the random signal, right? We saw examples of that the way that the random signal kind of behaves, or its kind of elements of its, we'll say, texture or features resemble the autocorrelation function. And then the other important thing is if everything's stationary, right, the Fourier transform of the autocorrelation gives the average power spectrum of the random process. And this is a place where people mess up. Okay, so I'll point it out again. The average power spectrum of the random process. If you take one example, you measure that random signal one time, and we saw this in examples, it doesn't necessarily look a great deal like the average power spectrum, because power spectra are very susceptible to the random variations. In other words, they're very noisy. But if you took a whole bunch of those and averaged them out, they would converge on that average power spectrum. And of course, if the average power spectrum goes to 0 or very low levels of frequency, then you won't see much of that frequency in examples from the random process. Okay. So this shows the kind of the average frequency content of the random process, but it will vary randomly. Okay, and the other thing we noted at the end, and this will come up today, is what we mean when we talk about white noise. Okay, so I want to reiterate this because this is going to kind of lead us to the next things we're going to talk about. When we say white noise, that's a way of communicating, the language of this field, that is a random process that is zero mean, has an autocorrelation function that is a delta function, okay? And remember that the and since it's zero mean, that's the autocovariance, and at zero lag, that represents the variance that we would see in that random process. And so for a white noise random process, the autocorrelation function is sigma squared, being the variance, delta of t, tau. Sorry, that's a tau. And its power spectrum, therefore, is a constant, because that's the Fourier transform of the delta function, but scaled by the variance. Okay. So when we say white noise, it tells you all that. And that's a thing you should be aware of. Okay, so we will talk more about white noise a bit later today. I'll throw this out there. I kind of threw it out there at the end. Did anyone think about this? What this might mean? This would be, so to kind of step back on the idea of white noise, right? That is kind of one extreme that we could possibly have. You have an autocorrelation function that's a delta function, right? As you start to kind of open that up a little bit, and I always like to think of this in terms of Gaussians, right? Because as Gaussians get narrower and narrower, they will approach a delta function, right? So let's think of that delta function and then being a Gaussian of like zero width, and then we start opening that up. Well, actually, I think I might even draw this. Okay, So let's say, everything's kind of covered up there. We kind of start from an autocorrelation function that looks like this, right? And then we say, okay, well, we kind of start opening that up a little bit. And making it broader and broader in terms of Gaussians, right? This is another, again, Gaussians are useful because of a lot of these kind of properties. So its power spectrum, starts out as that, but the Fourier transform of a Gaussian is another Gaussian, right, with kind of inverse width relationship. And so as it becomes wider and wider here, right, it becomes narrower and narrower here because we have less and less, less and less high frequency, we'll say. So what happens when we go all the way to the other extreme, right? With the idea that, oh, okay, then my autocorrelation function becomes an infinitely wide Gaussian, which is like a constant. So then its power spectrum is going to look like what?
It'd be a delta function.
It would be a delta function at 0. Now, what does that mean for its frequency content?
I mean, it's just at 0, so 0 frequency, I guess.
Right. So the only frequency we would have in examples from this random process is 0 frequency, right? So, and 0 frequency is a constant, right? A signal that, would basically look like that. So basically this says that if this, if you had this situation, you would have random signals that were all constant value. Now they could have different values, right? Each time you measure it, it might have a different constant value because it's random. So you could think of it as even like a random number that just persists through the time that you measure. This is not particularly useful in any examples I can think of. So, not a big deal, but it's a kind of a thought problem really about, okay, well, you can kind of go to that other extreme. And you have a whole continuum of possibilities if you think of them in terms of Gaussians. Now, obviously, we can have other autocorrelation functions that are not Gaussians. We've seen examples of that. Does anybody have any questions on that? So that's, maybe a little bit of a test of your understanding of the principles, but not in a practical sense, not really very useful. Okay, so that was the last thing I wanted to talk about that was in the slides from last time. So we're going to move on to the next group of slides that are associated with today's date. Okay. All right. For some reason, sorry, I can't seem to get rid of you. Okay, I guess we'll just have to live with it. Okay, so the thing I want to bring up now is this system model. And this is a pretty typical, model of, it's simple, right? But it encompasses a lot of the problems really that we encounter, or I'd say the main problem we encounter in signal processing. Okay. And that is, so there's a signal we want to measure, right? But there's some noise that gets added to it in the measurement process. And so the only thing you actually measure is G. Okay. And G is the sum of the thing we want to measure and something we don't want, the noise. So, you know, that's hopefully simple enough. I mean, in a sense, if you just take the T's out of there and say, okay, you know, any lab experiment, there's a thing you want to measure, but there's some variability associated with every measurement. You know, this is why, if you can, you take multiple measurements of the thing you're measuring in the lab and average them together, because that tends to reduce the effects of the randomness associated with the measurement. So it's the same idea in, you know, in that sense, only we're just turning them into signals now. Okay, so simple enough model, right? Now there's a few assumptions that we're going to kind of throw into that model, which are typical. I guess we encounter them often enough that this is probably the best place to start. So we consider f of t not to be random so much. Now we could, but either way, it's unknown, and we don't really know anything about it. Okay, at least that's, well, I'll step back from that and say, maybe we'll know something about it, but we don't know specifically what f of t is. But we are going to consider that we know n of t, or at least its random property. So n of t is random, so we can't know any particular instance of it, but we know how it behaves on average. And a way to characterize its average behavior is through its power spectrum, right? Knowing what frequencies are contained in the noise. Now, in the real world, the thing we often encounter is that f of t is effectively band limited. And by the term band limited, again, this is a, you know, part of the language in signal processing. So when we say that, basically, I'll say at some point, high frequencies, we'll say are not present. Now, what we mean by high frequencies, you know, varies depending on the system. But basically the idea is it has a low pass characteristic. In other words, it's going to have a characteristic that at some point is going to drop off in frequency. Okay. Now it may not be perfectly level up to that point and so forth, but you know, we won't worry about that too much right now. The main idea there is that past some frequency, we don't have any content really for f of t. Okay, and that's, you know, that's because of physics in a lot of cases and limitations in, you know, how you could build your measurement system. Okay. You can think, you know, again, I go back to imaging examples a lot, but in your digital camera, the pixel size on your little CCD detector that's in your digital camera, as well as the lens system, is going to ultimately limit the spatial resolution you can obtain, right? Your instrument ultimately, it can't get any better than a certain level, no matter what settings you use, because that's just the way the system's built. And physics says at some point, You can't build it to have, infinite resolution. So at some point, we're going to encounter where f of t is going to drop off in terms of its frequency content. N of t, the noise, is often going to be modeled as white noise because remember our discussion of statistics, probability and statistics, it turns out in a lot of cases that naturally generated noise that doesn't come from one specific dominant source is actually well modeled by white noise. And you can do measurements and confirm that in a particular instrument, but in a lot of cases it's true. And the other thing about the white noise that's important here is that it really is not dependent on the measurement. Okay, so the noise, basically you can think of it as an interfering source kind of coming in, and it doesn't care what the value of f of t is. It's just going to be there anyway. Okay. Now, this example doesn't always hold either, the noise being uncorrelated or totally unrelated to f of t, because in a lot of imaging where we're counting photons, it turns out that properties of the noise are dependent on the true image, true signal. So this doesn't always hold, but in a lot of signal cases, it does. So we'll go with it. And so as a result, most of the kind of raw, unprocessed noise that just basically comes into your instrument from outside is uncorrelated and white. Remember, not always Gaussian distributed. So, sometimes we have other distributions associated with that, but that's not, Gaussian isn't required for it to be white noise. We took a look at that example. Okay, so basically we have two kind of assumptions we're imposing on this model, right? That there's a band limit to f of t and that our noise is white. Okay. So the thing to do now is to see what happens. Okay, and so I'm going to add a slide here to draw on. All right. And now we can use color, so we'll do that. All right, so we're going to draw a kind of power spectrum frequency space. We'll call this axis signal power. We're looking at signal power as a function of frequency. And so what we're saying about f, the first assumption that we said we made, is that at some point, f drops off. Okay. And then what we said about the noise is that the noise is white. So it has to have a power spectrum that looks like that. This is its variance, right? Now, hopefully it's not too hard to recognize that we could prove this, but I think we won't take the time to do it. And this is because I'll use the term independent, but we say uncorrelated to mean the same thing. Okay. Hopefully you can believe that. If it's actually not independent and uncorrelated, we would have a kind of a cross-spectral term that would be the Fourier transform of the cross correlation of the two. But since the I'll say cross covariance of the two would go to zero, actually cross correlation would go to zero, then there is no such cross term in the power spectra. Okay. And so as a result, then SDG is just going to be the sum of those two things, right? It's going to look like that and kind of asymptotically approach that. Okay, so on the basis of, that relatively simple model, we've kind of just, I think, said a lot about this system. Okay. And again, this is a typical case, but you can extend this idea to other cases. So, what's the key thing here? Well, there's really, we'll say, two regions in this power spectrum. Let's use more color. And so this part of the power spectrum, basically our signal power is greater than our noise power. And then in this part of the spectrum, our noise power is greater than our signal power. Right? And so the question comes up, okay, well, if I'm going to process this signal, right? Because one of the points of, processing is to remove noise. Then maybe I'm going to put this through another system, like a filter system, in order to keep some frequencies and remove others. Well, what frequencies do I want to keep? Well, I probably want to keep the ones where the signal power dominates, right? And what frequencies would I like to get rid of? Well, I'd probably like to get rid of the frequencies where the noise power dominates. If you really think about it, right, at these frequencies, in the range where the noise dominates the signal is lost to me. Because I can't tell, remember, in the time domain, I can't tell the difference between signal and noise, right? They're both there mixed up in my measurement, and I can't, at any given time, I've got both signal and noise, and I can't parse the two apart in the time domain. Now I can parse them apart a little bit in the frequency domain, which is one of the main reasons why we even study these things in terms of the frequency domain, right? I can't pull noise and signal apart in the time domain, but maybe I can essentially parse them out in the frequency domain with this kind of observation, right? Understanding, okay, what's the power spectrum of my signal and what's the power spectrum of my noise? Now I can say, okay, so there are frequencies where maybe, I can identify that the noise dominates. And if I remove those, I'm removing more noise than signal. Now I'm removing a little bit of signal, but it's signal that is buried in the noise anyway. So sorry, I got to give up on that. But that's good, that's the basic idea. This is why we do low pass filtering for noise, right? Because we often encounter this situation. And so as a result, what kind of filter do I want to use? Well, in this situation, I guess I have another color here. I might want to use a filter that basically behaves something like this. And so in doing that, I'm keeping the frequencies where the signal dominates the noise. Now there's still noise in there, but okay. And I'm getting rid of frequencies where the noise dominates the signal. And notice that, where would I put the cutoff frequency of that filter? Somewhere around here, where the noise and signal are approximately the same power. Now, and again, that's not a hard and fast rule. It might, you might have reasons to move it one direction or the other relative to that point, but it'll be somewhere around there is where it would make sense. Okay, so this idea and that model that we encounter a lot kind of informs how we would approach this. And notice what happens if, suddenly we improve our measurement system and the noise level goes down. Well, if the noise level goes down, then the point at which, the two are equal moves up. And so I could probably permit a little more high frequency to pass through. So that would be good, right? On the other hand, if I get sudden burst of interference and the noise increases suddenly, well, then that operating point might actually go down in frequency, right? Okay, so this principle applies to a lot of different situations. Does anybody have any questions on this? I mean, this is basically what comes out of that model. Okay, and frankly, a lot of signal processing is going to, especially Fourier domain type signal processing is going to rely on the principle that, while we can't separate the good from the bad, I'll be general, we can't separate the good from the bad in the time domain, we hope to be able to separate them in the frequency domain. And since we can design filters that manipulate the frequency domain, we can design filters to separate them that way rather than working in the time domain. Okay, any questions? If you kind of understand everything we've been talking about so far, up to this point, that's good. Okay, and this is material that I'm, probably we won't have a homework assignment on this because assignment 3 is the last one before the exam. But applying this model is something that I often ask about on the exam. Okay. Now you can do variations on this. So we could have, for example, we could have a situation where we'll just do another one in kind of miniature. If we had another situation where basically SFF was within a band like that, but we still had white noise associated with it, right? You should be able to extend this principle to say, oh, okay, well, noise dominates signal here and here. So maybe those are frequencies that I don't need to keep. Okay, so even though this is a pretty typical case. It doesn't account for all the cases, but the basic idea is still there. Okay. If there are frequencies where noise dominates the signal, those are things that we're probably going to want to try to get rid of for the most part. Okay. Any questions?
How do you, how would you know like the variance of the noise? Like say you were trying to filter a signal.
Yeah, so it depends a little bit on the measurement system. If your noise is truly independent of your signal, you can kind of measure noise only without measuring the signal in a sense, by either not connecting it or something to that effect. Basically getting what I guess in imaging we would call getting the dark signal. But not all measurement systems are going to lend themselves to that. So there are other ways to do it. So maybe taking a lot of measurements and averaging them out, and then looking at the difference between the average and the actual measurements to kind of characterize the noisy variations. But for the most part, yeah, it's probably it amounts to taking a lot of measurements and then working on the basis of averaging.
Okay.
In order to, but that, the idea is what you'd like to be able to do is to experimentally characterize the noise of your system. Now, the other thing though, and actually I'll show an example of this in a bit, is, okay, the only thing I can measure is G, right? I can't actually measure F or N in my measurement system. But if I measure G and I look at its power spectrum and maybe average it over a few measurements, and it starts to do something, and it does something like this, where it kind of falls off and then levels off at some frequency level, well, maybe I can assume in that case that the model applies and this is the level of the noise up here. And then say, okay, well, I'm going to assume that's white noise. And so I'm going to derive from that, from the high frequency behavior of G, that the noise is white. If I can assume the noise is white, then I can basically just trace that line back and subtract to approximate what SFF is. So I could take the model and work it backwards in that case. And that is another way people might do this. Now, you're making assumptions as you do that, but with any model, you're making assumptions. And so it's important to, recognize where you could possibly go wrong in doing that, and the fact that you are making assumptions. But a lot of engineering is about applying models and making assumptions. So that's what we do. Okay. You just they just should be well justified. So actually we will look at an example like that. Any more questions on this element? Is that good? Okay. I don't have my 2-minute timer. This is a good time for a break. So there it is. So let's take 2 minutes. Okay. Time to come back. So I did, let's see. I had a request to perhaps move the office hour to 4 o'clock on Friday. So right now it's 3 o'clock. So we're going to take a little poll to see if that works for people in general. And so if you don't care, hit no impact, please. If it's better for you, note that. If it's worse for you, note that. If you don't even plan to attend office hour, no impact. Okay. But for at least one of our students, it would work better for 4 o'clock. So we'll see how that goes. And we'll let that run until everybody's in. Okay. Now, let's see. Back to the slides. Okay. Now, so, you know, the context of when we talk about noise, right? The context of noise is that noise is bad and it's something we don't want. And so the reason we don't want it is because it impacts the things, you know, that we want to do with the signal, to get information from the signal, right? And so, you know, in the simplest sense, right, we looked briefly at an example here, which is a cerebral blood flow velocity measurement. And, you know, with all of these little variations due to noise, you know, that might get in the way of, depending on what it is we want to do with this signal, and some of these spurious spikes, which are also noise, are things that we might want to do away with. And the poll is in, and so seems to be no negative impact, at least for those of you who are here today, for moving to 4 o'clock. So that's what we're going to plan on starting this Friday. Okay, I'll put that on the website. So we will move office hour to 4 o'clock. And of course, it will still be recorded. Now, right, so I was on that one. And so, you know, again, in general, it depends a little bit on what we want to do with the signal, but by filtering, right, we can go from this signal to this signal, which is somewhat less noisy. There are still some elements of noise in there, right? We can't get rid of it entirely because of this. And again, this illustrates kind of the basic problem, right? You're not, in most cases, you can't get rid of all the noise, right? You're going to have to retain some of it, and the best we can hope to do is to get rid of, you know, the frequencies where noise is dominant. Similarly, right, we're not going to be able to retain all of our signal if we choose to do some filtering. If we get rid of some noise, we're going to be getting rid of some signal, unless you have some, you know, kind of weird trivial cases where the noise and the signal are completely separated in the frequency domain, which is almost never going to happen. All right. The idea of artifact reduction is, well, we're going to just substitute the artifact for noise, for everything we've been saying about noise, and the idea in artifact reduction is going to be, hey, we're going to find what frequencies the signal we want dominates and what frequencies the signal we don't want, the artifact of some other signal, dominates, and work on that basis. Again, hoping that we can separate them better in the frequency domain than we can in the time domain. And then in feature detection, so again, this is a pretty easy situation, right? If you wanted to find these peaks or measure the, find each beat of this ECG signal, well, you might pick these peaks and just set a threshold. If it goes over this, that's a beat, log it and time until the next one. But if you have noise causing variations, then you can either spuriously come above your threshold or go below your threshold, and you're going to make an error, right? And so you're going to have to account for that. Well, smoothing out the noise might help in that event with feature detection. So, the kind of basic ideas of dealing with noisy signals permeate most of the tasks that we end up dealing with. Okay, well, let's kind of illustrate further with this model. Okay, and so if we take that ECG signal and add some noise to it, and this is white noise I'm adding, we get this. So it's pretty noisy signal in this example. Okay, and so this is the thing we measure, right? This is the underlying signal that we actually can't see because the noise gets in the way. If you look at the power spectra, and this is a place to, where things can fool you a little bit, you look at the power spectrum of the signal, and these are on the same scale, 2500, 2500, okay? You see that the signal, has a lot of power at a lot of frequencies. Notice that it is a periodic signal, and so it has elements of a fundamental and harmonics, although it's not perfectly clean in that way because it's not a perfect periodic signal. And it looks like the noise is, the noise power is very low compared to that, right? And so if you look at the total signal power of G of t on this linear scale, it looks very much like this, doesn't it? It looks like F dominates that power spectrum. So you'd say, well, why is the noise such a problem? Well, this is the place where the linear scale can fool you a bit, right? And so, as we've said before, sometimes you need to explore the semi-log scale, and the semi-log scale is more appropriate for visualizing certain things, and sometimes the linear scale is better. One is not always better than the other. But in this case, to get a closer look at what's going on, you really need to see the semi-log scale, and you can see that there's a lot of frequencies where the noise dominates in this case. And if I color them kind of the same way on the linear scale, you still, can see that, yeah, okay, we have a range of frequencies where the signal seems to kind of dominate the noise, but then up here, everything's green, right? Or the noise dominates the signal, but you can't really, on the linear scale, you can't appreciate how much by several orders of magnitude, okay? And what we see in the time domain is, effectively the integrated power of all of that, right? And so if you were saying, okay, what's the total noise power? Well, the total noise power is the integral of the noise power spectrum. And what's the total signal power? The total signal power is the integral of the signal spectrum. And, it's a little hard to say on this with a semi-log scale, but, I'd be willing, and I didn't calculate it, but I'd be willing to bet that because there's so much more noise power at all of these frequencies, the signal to noise, the total signal power to total noise power ratio is probably pretty low for this signal. Okay, because of all that. And by applying a low pass filter, then we could improve that ratio substantially. Now that's not, you know, again, depends on what you're going to do with the signal, and that's not the whole game necessarily, but you know, it has a lot to do with what we're trying to deal with in many cases, which is, you know, let's reduce the total noise power. And so that's a justification for doing that. Okay. And I guess the other thing is, okay, if we look at, I did not plot G in this case, but G should be the sum of the blue and green. And so if you looked at G, it would basically kind of come down, and then this power spectrum would kind of level off. And you would probably be justified in assuming that that's the white noise, and that's the white noise power level. Okay. That's applying the model to make certain assumptions. Okay, well, we said white noise, right? But what if the noise is not white? Well, if the noise is not white, you can still apply the same principles again. So I'm going to go back to this situation and do another variation on it, which is to say, okay, well, what if we have a different situation where, well, I guess we'll do something, let's see, what would be interesting. Well, we'll give our signal kind of this property, right, SFF, and then say, the noise is not white. Let's do something, you know, weird with the noise and say, okay, the noise kind of goes like that. Well, you still have the same idea, right? If you can estimate what the noise power spectrum is, right? When we, you know, the convenience of a white noise assumption, other than the fact that it applies in a lot of cases, is that, okay, well, because, you know, we don't need to know a lot about its power spectrum, right? But if you say, okay, well, the noise is not white, I happen to know this from measuring my system, and maybe it behaves like this, well, the principle is still the same, right? I want to know what frequencies are dominated by the noise over the signal, and those are the ones that are less desirable. Okay, and so, you know, you can apply this in a lot of different ways, and it doesn't necessarily require that the noise be white noise. That's the point, but you're going to need a little more information in that case, right? Just as, you know, in situations like even this situation, you're going to need to know something about your signal. You're going to want to know what the, you know, what the typical power spectrum of your signal is, or you're going to make some assumptions about that in this case. Okay, so that's the basic principle, right? That's why power spectra are important. That's why power spectra of random, average power spectra of random signals are important. And I guess that's another point to reiterate. This is the average power spectrum of the noise. And so it doesn't mean that, you know, it's going to look like this every time we make a measurement. And so by setting the cutoff of the low pass filter here, you're trying to do the best you can on average, right? And that's the thing to remember when we're dealing with randomness, is the best we can do with random stuff, because we can't predict any particular case. The best we can do is to try to do our best on average. And so everything's going to be based on, you know, averages and things. And so in some cases, you know, particular instances, particular measurements of the noise may be a lower cutoff or a higher cutoff will get you more, a little better signal to noise ratio. But then on the next instance, maybe not, it goes the other way, and we're kind of dealing with that randomness, right? And so this is one of the things I'm trying to get you, it's a little different way of thinking that, not everything is deterministic anymore. But the idea is we're going to do our best on average, and sometimes it's going to work in our favor, and sometimes it's going to work a little bit against us, but over the long run, that's the best way to go. Okay. And that's how we work in engineering. Okay, does anybody have any questions on that? This is basically the kind of last thing. We're not actually going to discuss assignment 3. I'm going to leave that as a separate supplemental recording. So the next thing that I would do is go to that exam question. Let's see. Okay, now this is from years ago and was an in-class exam. So questions, in an out-of-class exam, things are a little bit different, but not necessarily a lot different. And so, a question like this applies, and I think still could work as an out-of-class exam. Okay, so here's what we have. Below, a portion of the Fourier transform magnitude, okay? And this is a respiratory airflow signal, so that's an important piece of information, taken with 512 samples over a period of 10 seconds. Sometimes I give you information that is not important. So it's not necessarily true that every piece of information in the question is important. Okay, then I note about the frequency scale. Note that the numbers along the x-axis are the discrete frequency terms and are not MATLAB format. I took the MATLAB index and subtracted 1 from it to get these. So I'm telling you, I don't, even though I always tell you to label your graph with units, I purposely don't give you units here, okay? Because I want you to tell me what, essentially use what you know to interpret what the units should be. Zero term represents a frequency of 0. So I want that to be very clear. Okay. Okay. Now, usually these are kind of a setup to a question with a couple of parts to it. This one has 2. Give your best estimate of the period of respiration in this subject in seconds and show how you determined it. Okay, so a couple of things kind of work into this and a couple of things you should be thinking about in this. Okay, this was a respiratory airflow signal. Respiratory airflow is periodic. So that's one thing that should kind of, and of course, we refer to the period of respiration in this subject. So this should be a signal with periodic elements to it. Now, what did we say about periodic signals? Remember, the Fourier transform of a periodic signal has, well, a Fourier transform of a perfectly periodic signal, right, where the waveform is the same in every cycle and it's identical, will only have elements of the fundamental frequency and harmonics. A perfectly periodic signal. Well, of course, if we measure from actual living beings, we're not going to get a perfectly periodic signal, but we should get something that has some periodicity to it. Okay, and so you should recognize in this that, okay, this, and this look like elements of that periodicity. In other words, there is a fundamental and integer multiples of that. This one occurs at about 13. This one occurs at 26. And so the next one would be at 39, and it does. Okay. So that's the first kind of thing you should recognize, is that that's where the periodicity is. Now, the fundamental frequency gives us the base rate of repetition for that periodic signal, right? And so it's going to be 13 frequency units, whatever that is. Here it is. So this is a thing. Apparently Zoom has annotations, right? Okay, and so the idea is that's 13 units, that's 26, that's 39. Those are integer multiples, which is what we expect from a periodic signal. But the important one is 13. And by the way, just for future reference, the fundamental doesn't have to be the tallest one necessarily, okay? It can still be periodic if this one, you know, had a peak down here somewhere, and the second one was the highest. What you're looking for are these kind of spikes that are separated by integers, and the fundamental is the lowest one of those. Okay. In this case, it is the highest, and often it is, but not always. So I want to make that clear. Okay, so it's 13 units. And so now the question is, okay, what are my frequency units? Well, this is the thing I expect you to know, right? If you take MATLAB index and subtract 1, then the frequency units will be cycles per recording period. Okay, so that's the thing you should be aware of. And again, you pretty much just have to know that, although it's justified by some things that, you know, we talked about with basis functions and things like that. Okay, and the recording period was 10 seconds. So this is cycles for 10 seconds. So this fundamental frequency then is actually going to be 1.3 cycles per second, which is hertz, but doesn't matter. But we asked about the period of respiration. So period is seconds per cycle, right? How long is each cycle? And so the period for that is 1 over 1.3 seconds per cycle, whatever 1 over 1.3 happens to be. Okay, and again, I want you to show me how you got there. So you should be kind of explaining that a bit as you get to it. Okay, well, this is an interesting thing about those Zoom annotations, right? They don't move. Okay, any questions about that?
So I have a question.
Yeah.
So you said that it's not necessarily the case where the fundamental frequency is the highest, right? So
Right.
if then the next highest would be the base rate of repetition.
No, and so that's the point that is important. Okay,
Okay.
it's always so when you have a periodic signal and you have, you know, these kind of you know, we'll call them like delta functions at spaced out at integer intervals in the frequency domain. It's always the one closest to 0, that is the fundamental and gives you the base rate of repetition.
Thank you.
Okay.
Got it.
Yeah, and so that's that's why I wanted to warn you about that, because that's a mistake people make sometimes. Is, if this one was lower than the 26, they would use the 26 as the base rate of repetition, but that wouldn't be correct. Okay. So now my annotations are just going to get in the way, so we'll do that. The second part, so the period of breathing for this subject changed near the end of the recording period. Did the period increase or decrease, and how do you know? So this one requires a little, you're not calculating anything here so much, but kind of thinking about your understanding of how things should work. Well, if the period changes, right, we're not going to see elements of these guys anymore. We're going to see elements of different frequencies. And the best element of different frequencies, because they are higher, they have more signal magnitude in them, are these little bumps on the high side of each of our frequency elements. There, there, and there, right? And so the idea really that is kind of reflected in that is, okay, if the period changes, then what we might be seeing are elements of a fundamental kind of shifting upward and elements of that shift upward in harmonics. So if that was true, then we'd be saying, oh, well, then the frequency is increasing, right? Which means the period of respiration is going to decrease because it's the inverse. And so that is probably the best way to answer that question. Now, and I want to make a little bit of a point here that sometimes on exams, right, there are questions where there are good answers and there is a best answer, right? And the best answer is the one that gets full credit. However, it's a good idea, whatever your answer is, to justify it, because there are cases where more than one answer is okay, actually, and gets full credit if well justified. All right. In other words, if you can talk like you're making sense and understand and show that you understand the principles. Okay. So, don't be shy about trying to justify an answer under certain conditions. And so if, it would be hard, in this case, it would be hard to argue, well, okay, if it shifted down, then you get an element here and an element here and an element here. And that's more likely, it's hard to argue that shifting this way was a more likely event than shifting this way, where there is more element on the high side of these things. But you get most of the credit if you argued that in a reasonable way. Anyway, you get the idea. Okay. Okay, and so that's what there is to this. I can guarantee you that on at least one occasion on the exam, and maybe more than one, you will have to, convert MATLAB style or MATLAB based frequencies into real world frequencies. Okay, that's always there. And So you will definitely have to do that. And so, make sure you know how to do that, because it's one of the most fundamental things that we deal with in this class. By the way, going back to, what we had here, notice that the 512 samples was actually not important. You didn't use that piece of information. What you needed was the full recording period of 10 seconds in order to calculate this. Since it had 512 samples, there was more to the Fourier transform than what I showed you, right? I didn't show you the whole thing because this only went up to 50, and there was, there was going to be unique stuff all the way up to 256 in the frequency space. But I didn't give you that, and you didn't need it. Okay. All right, we're almost out of time. Any last questions? Does anybody want to make a motion to move the exam to Tuesday rather than Thursday next week? Okay, then I think we'll leave it at Thursday. On Wednesday, I might poll you next time about this. On Wednesday, I will schedule a special Q&A session, not a review session in the sense that I'm going to come in and review material, but kind of an office hour type of thing where you bring questions. If you don't have questions, then we don't do anything. Okay, basically. And we'll do that on Wednesday sometime, not sure when that is yet. I'll poll you about that and see. And sometimes we have to do, schedule 2 separate times to give everybody an opportunity, and that'll be okay. My Wednesdays are not that busy, so I'm sure we can find times to do that. Okay, and I do that the day before the exam because people don't look at it, look at the material until the day before the exam these days. Okay. All right. Any last questions? All right. Thanks, everybody. Good to see you. We'll see you on Thursday.
Thank you.
Thank you.
Thank you.